Alright, so we're starting with like the theoretical idea of court case examples. So first of all, if there is a court case for something, why is there a court case in the first place?
Something bad.
Okay, so just because something bad happens, does that mean I'm going to have a court case? So, do we know that someone broke the law?
No.
So, like, if a person gets sent to court, why did they get sent to court?
There's a possibility that
There's possibility. There's evidence. There's someone thinks they did. So let's just write it as someone accuses them of something, which is a weird way to say it. That part doesn't really matter. So, like, if I do something bad and nobody knows I did it, I'm not going to go to court. It's that someone else sends you because something happened, blah, blah, blah. Alright, the person who took someone to court, like if I took somebody to court, I think that they are what? Guilty. So these are going to be really quick things that we're just going through. So I think they're guilty. Well, I took them to court to kind of answer the first one. How does the person prove that they're guilty? By having sufficient evidence. So we have enough evidence to be able to prove them. Alright, so this is something you hear a lot. The person that is taken to court is considered what at the beginning of the trial? Innocent until proven guilty. So this part is kind of really quick and a little bit repetitive at this point. What happens if there is enough evidence? They're considered guilty or convicted, whichever way you want to write it. What happens if there's not enough evidence? They're acquitted, not convicted, whichever way you want to say that. This part right here is just kind of conversation pieces. So saying it, the same thing we just said from the other side. If someone is convicted, it's because what?
There's enough evidence.
There is enough evidence. If someone is not convicted, does that mean that they were innocent? No. It only means what? We didn't have enough evidence. They, whatever you want to say. So this whole concept is the concept of most of statistics, but especially chapter 9 that we're getting ready to start. A claim is made, we test the claim. If there's evidence, so initially they are considered innocent. If we have enough evidence, then they can be guilty. If we don't have enough evidence, that means we let them go. That same concept applies for everything that we're doing today. So we're going to have a null hypothesis and an alternative hypothesis. Your null hypothesis is H sub 0. Null means empty set. That's where your 0 comes from. And then alternative hypothesis. I used to write this as a lowercase a here. Don't write it. but that starts to look a lot like a O when you're writing them really small. So I think it's easier to deal with capital A. You will see other textbooks that use a 1 there, and you'll see textbooks use a lowercase a. I think our textbook uses a lowercase a, but it's a lot easier to tell the difference when you're using a capital A.
Why would you use O then for null?
Null means empty, and empty is 0. So like, that's where the origination of that one comes from. So in this is the initial claim, but I don't want you to think too particular about that. So in the court case example, what was the initial state of the person being brought to court? Innocent. I call this the initial claim, but sometimes it's or previous current value. I'll be able to explain that one better when we start getting into problems. But I do want to come back and make that point again. The alternative hypothesis is what we're trying to prove.
Wait, so the null is the initial claim, or it's
The null is kind of the initial claim. But sometimes it's the previous state. And you don't have to write this parentheses. It's how we're trying, well, I guess I do want you to write that. How we're trying to prove the null hypothesis wrong. In the court case example, that doesn't make sense because it's like, well, we're trying to prove guilty. That's how we're trying to prove wrong. But in math, it's like less than, greater than, not equal to kind of thing. Right. So we would be proving it is not equal to correct. Yeah. It would be in terms of inequality, it'd be not equal.
Which is
not equal to. Did yours say general layout for hypotheses instead of that? Okay, good. So your general layout for hypotheses, we're always going to have a null hypothesis and an alternative hypothesis. And so this is very basic, but it is going to be the giant first premise that we talked about. So here we are going to have some parameter plugged in. What are our possible options for parameters? Give me some possible options for parameters. Mu, sigma, p, that type thing. Whatever we write there, we're also going to write it again here because we're going to be talking about the same thing. For the sake of our class, this is always equals. And then we're always going to claim that it's equal to some number. Whatever number is here is also here. So if you claim to be an A student, I could write like your grades equal A. But I might be trying to prove different and prove something like your grades are what? A. Less than. Other options could be what? Not equal to or greater. So those are our three options of what to put there. Either greater than, less than, or not equal to. So has to be a parameter. Cannot be a statistic. Null hypothesis has to be equal. Alternative hypothesis can't be equal. The parameter that we used up here has to be the same one that we use here. The number that we use in the null hypothesis has to be the same number that we use in alternative. So this is the first very, very basic thing of the lesson for today. Is tell me what's wrong. So in this first example, What is wrong there? What should I write beside that?
Needs to be framed.
Needs to be a parameter. Needs to be a parameter, or this is a statistic which is not a parameter. What's wrong with the second example?
It has to be equal on the top.
I know you probably don't have much room. You might need to come out here and do like that. So my equals has to be with my null hypothesis. Something that's not equal has to be with the alternative, so I could just switch those. And then what about my third example? These should be the same number. Alright, so the whole left side on the front is just talking about very generally what it is we're going to discuss and the layout of the null and alternative hypotheses. So now we're going to go through a whole example, but kind of in theory and not exactly specific to what we're doing, but to get the idea of what's occurring through a problem. Alright, a friend says that he can run a 5-minute mile, but you do not think that he is that fast. So you want to time him and see, how could you write a null and alternative hypothesis for this scenario? Let's write up top, I know it doesn't ask us, but let's go ahead and define our parameter. When you do, I think it's going to be your homework today, it's going to say write the null, alternative, and define your parameter. So I want to go ahead and do it that way. So we are talking about what parameter here? Which would make sense to be talking about what parameter here. What did we say our options were for parameters right now?
Mu sigma.
U, sigma, and P. Well, if we're talking about he runs a 5-minute mile, mu. So let's go ahead and, I think you have some room up top. Mean time it takes him to run a mile. No, I'm gonna put in minutes. Like I said, that was kind of an afterthought, but since your homework didn't ask you to that way, I wanted to cover that. That's what it means when it says state null, alternative, and define your parameter. Alright, so my null hypothesis is the claim, which is what? Mu. It has to be, and 5 what? And it's actually a 5-minute mile, but because we're saying 1 mile in. Right. It just wording with the way we defined it, so we can just do this in a minute. Alternative, and I know you could do this, because this is mu, this has to be what? Because this is 5 minutes, this has to be. So the only decision you actually have to make in alternative is what goes here.
Well, for him to prove it, are we trying to prove him wrong?
So we do not think he is that fast.
So we want to clock him and see over 5.
So we are saying
Mu is less than.
we want proof in this direction. We want proof that he is greater than. Yeah. Now, back to when I said your initial null hypothesis is the initial claim or the previous current value. If I did this one and just said, I didn't say what your friend said he was. I just said something like, I think my friend runs slower than a 5-minute mile. I would get this same thing without an initial claim. Does that make sense? So like I'm calling it the initial claim because most of the time it will say something like this.
Would you have an initial claim at all, or would you just do?
You would be testing that it was greater than 5 minutes, which would make your null end up being 5 minutes.
Okay.
Alright, so we're gonna use a lot of hypotheticals here. This is just me saying I'm gonna kind of read through the conditions portion of things. Let's say it is known that the mile times that he runs are fairly normally distributed. Let's pretend that we also know his mile times vary from the actual mean by an average of about 15 seconds. That's our what? Sigma. So 0.25 minutes is our sigma. Let's also pretend that his mile times are independent. So I'm basically saying I'm not dealing with conditions right now. Alright, now this is a bit of a stretch to apply these things. As far as I wouldn't expect you to look at this problem and be like, oh, this is how I would do it. But I just need you to kind of follow with me for right now. So let's make a distribution based on his claim. So this is all based on the claim. What would the center of his distribution be? And I don't really care that you have minutes there, but we're going to put it there. What about spread?
Sigma equals F.25.
Again, I'm including units right now, but usually in a problem it gets kind of messy when you include units within. And what about shape? I gave you that part. Alright, so because I know all of that stuff, I can draw a curve. Really start copying and pasting in. What value goes there? 5. And as I go one line each direction, how much do I go? 0.25. So this is 5.25. I know y'all's doesn't have much room. You might even have right sideways.
We have a lot of different.
I got it. Oh, okay. Maybe it's the next one. Maybe not. Alright, so we understand that, assumingly so, with all those conditions that I told you ahead of time, which you probably wouldn't know if you were just having a conversation with your friends, his mile times would fit in this distribution. So what happens when we're doing one of these is we basically say, okay, as statisticians, hypothetically, let's just pretend that I believe you and everything about this is true. So I'm going to do everything to say that what you did is true and then see what happens from there. So we are building this based off of everything that he says is true. So what kind of value is 5.25 right now in this scenario? So if I had to write something like, what would be our best guess of what goes there? Don't think about this. Just think about he ran once, and it was this. So we timed him running a mile. We timed him once.
X.
So that is just x, as opposed to what? And why is it x and not x bar? X bar reviews multiples. This is just one individual value, not a mean of a sample.
What do you mean X bar?
Because it's just an individual value. Alright, so we're going to draw this on the curve. So we're just going to draw where 5.25 is here, which is there. So now we have to decide where to shade. Well, where did I think he was going to fall in his distribution?
Wait,
Where did I think he was going to fall from his claim?
What do we say for what kind of value?
We're going to fall in. Oh, that's just x equals. What kind of value is x equals 5.25? So we think that his is going to be what in his claim? Greater. So if it is greater than, from this line, shade to the right, because the, where did I find, I didn't need a blank this big. Where did I find that I wanted to shade to the right? What did I literally just scroll back to? The alternative hypothesis was what? So I'm trying to very clearly spell things out today, and hopefully I'm kind of being slow. So if our alternative hypothesis was less than, we would shade which way? To the left. So I'm just showing that's where you would get that information from. All right, so let's actually go ahead and take it and shade it. So this shaded area represents a what? We've dealt with this a lot in the past. Probability. Alright, so the way we take our perspective here is I always think that statisticians are just like complete sarcastic people that say, okay, whatever, I'll believe you. If I believed you, and if you were true, and if I recorded you and you actually got this high, I can tell you how likely it is that that would happen. How likely it is to get a rare occurrence like that. So, how would we write this for this problem? Well, p parentheses, what did we say that the value was that we were dealing with? So, we're writing p parentheses x is what? Greater than the 5.25. And y'all have a lot more, y'all don't have anything below this, right? Okay. So let's go ahead and bring in other chapters from there. What can I do with that? Convert it to a z. So what do I put in my z equals equation? So my value, which is 5.25, minus the mean, which is what? Divided by?
Value minus mean over what?
Standard deviation.
Is it sigma? Or is it
Yeah, so this one in this case.
x minus mean over sigma?
Mm-hmm. Well, I shouldn't need help there. How much do I have on top? Divided by 0.5, which gives me. Then I can either use my yellow sheet or I can use my calculator with second distribution, normal CDF. Either way you do it. You can use the yellow or second distribution, normal CDF to find the area of that part. It's about 16%.
Wait, how would you?
I did it that way before, but then I did my other one not empirical rule and I didn't want to.
How would you use the yellow sheet you'd be looking for 1.10?
Yeah. So this is something we've dealt with a bunch. Just applying it here, I'm finding that shaded area, which is to the right of 1. So if I look it up in the yellow sheet, what do I need to do with that number? 1 minus that. What he was saying, don't draw this. What percent is between here and here? What? 68. So if this is 50, This is 50. This is half of 68, which is 34. About what percent is left over for here? About 16% using empirical rule.
Wait, I'm still lost on the yellow. I'm looking at the yellow sheet. How do
1. What do you get as your area when you look up 1?
0.8413 or 0.7064. Yeah. Oh wait, no. 0.8. Okay.
And what do I do with that?
1 minus.
Which gives me which is about 16%.
And how do we do it in our calculator?
You just go to second distribution, normal CDF. Your lower bound is -1 E99. Your upper bound is 1, and you should get the same thing. Alright, so this is saying that, okay, let's pretend I believe you. Let's pretend you run a 5-minute mile. Let's pretend that your standard deviation is 0.52 mile, 0.25 minutes. Then the likelihood of this occurring, which is something this far away from what you claimed or farther, would happen about 15.86% of the time.
Sorry, real quick. Even if we use the calculator, we still have to do the 1 minus, right?
If you do it that way, yeah. Or you'd go from 1 as your lower bound to 1 E99 as your upper bound. Alright, so understand what I just said there. So if I believe you that your claim is true, this means you actually run a 5-minute mile, then the likelihood of you running this slow or slower, or this high of a value or higher, would happen about 15.87% of the time. You with me? Alright, so at that point, would we tell our friend he's a liar? 15, 16% of the time, I mean, maybe bad day, okay? We'll give you the benefit of the doubt right now. Alright, flip it to the back. Alright, so now we have scenario number 2. So we timed him running, and so pretend scenario 1 didn't happen. We timed him running 2 different mile times. The first time he ran a 5.2. The second time he ran a 5.3. Well, what are we actually going to do with those? Average them. So we end up getting an X bar of.
5.25.
So I'm purposely comparing it to the one we just did. So this is different because this is an X bar and not an X. Because the other one was one individual value and this is a sample mean. Alright, so now we have to talk about our shape, center, and spread like it was last chapter, or the chapter before. So what do we write as center when we are dealing with a bunch of X bars? Mu of X bar, which is the same thing as the population mu, which in this scenario was claimed to be what? That's directly from chapter 7.
What made us pick 5?
That was still, we're still using the same claim.
But just not.
That's still from, yeah, back there. Alright, so when we are dealing with X bars, a whole graph of X bars, what do I write as my spread? So just like this, sigma of X bar, what is my equation for sigma of X bar? That was last chapter and the chapter before. Well, what do I know my value for this problem is for sigma? 0.25. In this particular example, what is my n? 2.
How do we know it was 0.25?
That was still from given the problem we said, let's pretend that we know that. And let's do it 4 decimals just because I usually do things 4 decimals. And we get what? Point what?
1768.
And then I want to make the connection here with the exact same thing we did with chapter 7 and chapter 8. Since what? Since it is stated that what?
That it is my function.
And I'm going to write it, which is saying the exact same thing. Since it was stated that the population distribution is what? Then what?
In the shape
I think we can use normal approximation.
Normally, we introduce another word conditions.
And so 10% condition falls under independent, and then that's why I threw that part in there. Or you could say, you could go through and say, I can make them run more than 20 times, that's fine too. You're saying that usually when we do this, we have to do 10% condition. 10% condition technically falls under independency, which is part of why I made this weird claim. But also I could go through and talk about making him run, he could run more than 20 times, and that would be fine too. I'm trying to just like take that part out of it right now. Alright, so we're gonna draw a number curve. It still originates based off of the claim. Which means it is still centered where? Still centered at 5. But now, how much are we adding and subtracting each time?
0.1768.
0.1768. And this is where I was saying it might be hard to put it in there. So, as my sample size increased, this goes back to chapter 4, what happens to my distribution? As my sample size increased, so I had 3 things, center, shape, and spread. Again, this is just review from past chapters. As my sample size increased, what happened to my center? Stayed the same. As my sample size increased, what happened to my spread? It what? It decreased, it got smaller. And then what happened to my shape? It was already normal, so or approximately normal, so it's still approximately normal. Okay, so what kind of value do we get from these 2 mile times? We already wrote this somewhere. What do we get? X bar, because we're dealing with 2, so we gotta find the mean of them. So let's go ahead and draw that. Well, what am I going to write here this time? We're going to shade to the... Is any of this going to change? Because our claims are still the same. So we're still going to shade to the right because the alternative hypothesis was greater than. So now our line's going to be somewhere in here.
And we're trying to prove the alternate.
We are
Like, not the opposite of it, right?
we're trying to prove evidence of the alternate. Because we're trying, like, innocent until proven guilty. We're trying to prove evidence of being guilty, and guilty is your alternative. Alright, so we're gonna have a line just somewhere in here, shading this way. And this shaded area represents a what? Probability. So P parentheses what? X bar is greater than 5.25. I do what with this? Convert it to a z. Now this is where we kind of, like the last one was x minus mu divided by sigma. A lot of times we quit writing what really goes here because really x bar minus mu of x bar divided by sigma of x bar. So my value is what? 5.25 minus, but now it is divided by and we get what with that? And just because we usually write z's to 2 decimals. So is that going to be less than or more than 15.87%? Is that going to be less than or more than 15.87% that we had before? Less than, because we went farther to the outside. I don't know what I get here. What do I get from that answer? So now, if I recorded him running twice, and his averages were 5.25, now the likelihood of that happening is only a little bit less than 8% of the time. So obviously, the more that I do something, the better it is going to be, easier it's going to be to prove against them. When his time was 5.25, and he ran once, that was likely to happen a little bit over 15% of the time. But if I only make him run one more time, and now he runs twice, the likelihood of him being at that same value is knocked down all the way down to about 80%. Okay, questions with any of the stuff we've gone over so far? So I've gone over it in a weird way, but this is essentially what we're doing for all of chapter 9. Does it go straight into the practice ones for y'all? Alright, I do want to go ahead and do this right now. You're answering 1 through 9. I just want you, it's mainly like write the null and alternative hypothesis, except number 1 says what thing's wrong about it. And a couple others ask you something a little bit different. But go ahead and do 1 through 9 really quick. Shouldn't take very long.